Hi, this video will cover section 4.1, radian and degree measure. The objectives for this section are to describe angles, to use radian measure, to use degree measure, and to use angles to model and solve real-life problems. So first, we're going to define what the word trigonometry is, and it is derived from the Greek language, and the word trigonometry means the measurement of triangles. Initially, trigonometry dealt with relationships among the sides and angles of triangles. An angle is determined by rotating a ray half-line about its endpoint. And so to demonstrate this, I'm going to draw a ray, which is a line, but it does have an endpoint, so it's not a line because a line will have two arrows. And so if that is our ray, and imagine you rotate that about the endpoint, and in this way, this direction, it is considered to be counterclockwise because it is going in the opposite direction of your clock. And so if we do that, whatever angle, or actually the rotation here, that could be considered to be the angle, but we will get into more examples like that as we go on. So based on what we discussed on the previous slide, we are going to have the ray that I drew previously, and that will be occupying or corresponding to this vertex and the initial side of an angle. So that is what we call the initial side. And the terminal side is going to be this ray right here. To have an angle in standard position, as we see here, this is an angle in standard position. In fact, this one here, and you can see there is an initial side, and that one happens to be on the positive x-axis. And so after that rotation, and also considering the vertex to be the origin, that is very important. And if we go in the same direction that I discussed previously, counterclockwise, so counter because it is going in the opposite direction of the clock. So we have here the terminal side, and that is what we call an angle in standard position. So always the initial side is going to be the x-axis. So when angles are going in the counterclockwise direction, they are considered to be positive. But when they go in the clockwise direction, and that is also starting from the positive x-axis, they are considered to be negative angles, and that is going to be very important throughout the whole course. So to denote angles, we use Greek letters, and the ones that are used, the most commonly used are alpha, beta, and theta. Also, we will be using uppercase letters such as A, B, C. Those are the most commonly used. So on the figure that you have 4.4, the one on the right side, it is showing us this angle that starts on the x-axis, so it is on the standard position, and then we rotate counterclockwise. In the terminal side, is right here in the third quadrant. So that is the angle denoted by the Greek letter alpha. Now, we also have another angle from that same Cartesian plane that also starts on the positive x-axis, but the rotation is counterclockwise. Sorry, clockwise. So it's going in the same direction as your clock. And that angle is denoted with the Greek letter beta. And that would actually be a negative angle. Now, if we move on to the right side, we have an angle that starts here on the positive x-axis, rotates in the counterclockwise direction, and that will be the Greek letter alpha, and that angle will be positive. But we have another one that if we go start again on the positive x-axis and then rotate in the clockwise direction, and so that angle will be negative, and it will also be greater than 270 degrees. Well, I guess you could consider it smaller because it will be more negative, but we will discuss that as the semester goes. So those two angles that we were discussing, and let's consider this first one, case one. And so for that one, alpha is a positive angle and beta is a negative angle, but because they do have the same terminal side, they're considered to be coterminal. Now, on this other case, we do have a positive angle that would be alpha because that it goes in the counterclockwise direction, and we also have a negative angle, and that would be beta. It goes in the clockwise direction. And so those two have the same, first of all, the same initial side because it is the positive x-axis, but also they do have the same terminal side. And because of that, we consider them coterminal. They do have the same ending side. One very important measure of an angle unit that we will be using will be radian measure. And we determine the measure of an angle by the amount of rotation from the initial side to the terminal side. One way to measure angles is in radians. So we're not going to only use degrees, we will be using radians, and this type of measure is especially useful in calculus. To define a radian, you can use a central angle. A central angle is defined by an angle that has its vertex positioned at the center of a circle, like we can see here on the image to your right. And so we start here. This is our initial side on the positive x-axis, and we do have our terminal side here, and is denoted by the letter R for radius. So in this angle is positive because it's going in the counterclockwise direction, and we are going to call that angle theta. So theta is a central angle. And so if we consider the angle from here, a central angle, by definition, because it is a central angle, the arc that we have here, the length of this arc, or like a segment of the circumference of a circle, is also gotta be the same degree angle measurement. Let's call it that. And so at that point, the radius, this segment here, if we were to take that straight line and curve it so that it goes along this arc, well, not that one, but the one that is actually on the circumference, it will be the same length. And so based on that, we define that is 1 radian. When the radius being curved around the circumference, it's the same length. So 1 radian is the measure of a center angle, theta, that intercepts the arc, an arc S, that is what with the letter we will use to denote the arc, equal in length to the radius. So that's what I was saying about curving that straight line, the radius, and placing it around the circumference. And so algebraically, this means that theta, which is the angle, remember I told you that same arc, I will try to draw it here again. So this angle measure is theta. And that will be the same as the length of the arc, which is denoted by S again, and divided by the length of the radius. So this is R and this is S. And so whenever the arc and the radius are the same, that is when we can say that the angle measure is equal to 1. So if S is equal to R, just to have an example with numbers, let's use 3. So 3/3 for S over R, it will give us a 1. So that will tell us that the angle measure is 1 radian. And we will be converting degrees to radians and vice versa. So once we do that, it will start making a little more sense. So based on that definition, we have that the circumference of a circle, you could find that by multiplying the pi, pi times the diameter, or because the diameter is considered to be 2 times the radius, that could be also a way to calculate the circumference. So just to write it based on the commutative property of multiplication, I can move the 2 to the front, and this will still represent the same. So that will be 2, and then pi is also a constant, so it's going to go next to the number, to the integer, and then we're going to have r, which is the unknown variable. So that will be the radius, the length of the radius. So it follows that a central angle of 1 full revolution, and when we say a 1 full revolution, I want you to imagine an angle in standard position. So we start on the positive x-axis and we go in the counterclockwise direction so that the angle is positive. So we will go this way, and 1 revolution will be 1 full circle. So once the initial and the terminal side are the same, just 1 circle. Because we could go more than 1 turn or more than 1 revolution, which we will pretty soon. So what that means is that the length of that, the arc length of that, so imagine everything that is here in red, that will be S, that will be the whole circle. And just like we use the formula, we've been using the formula for the circumference of a circle, 2 pi r, that will be the length of the full circle. And so a lot of things that we'll be doing in this class will also be related or will be derived from that formula. So just to imagine what is a radian. Now, since we know that a full revolution of a circle is actually 2 pi r, so imagine if r is equal to 1, let's just call it 1 unit. So that would be the length of this radius. In fact, all of them are the same length of the radii. So if we say from the previous slide, the whole circumference of this circle is going to be the whole arc length. The arc length of the whole circle is going to be 2 pi r. And because r is equal to 1, that is going to be 2 pi times 1, which will be equal to 2 pi. So what we have here is something that we call the unit circle. And we call it the unit circle because the radius is equal to 1. And so in that case, that length of this radius, if we curve it around the length of the segment of the circle, which we call the arc length, that would be 1 radian, which is here. Now, if we do that again, if we were to repeat that length, that arc length, this will be 2 radians. And then once we do it a third time, that will be 3 radians. And so if we do it another time, 4, and that will be 5, and that will be 6. And so I want you to notice how there is a little space here that we haven't covered. And so that will be that 0.28 of a radian. So once we put those 6, remember it was 1, 2, 3, 4, 5, and 6, plus the 0.28, that will give us 6, approximately, actually, not exactly, 6.28 radians. So you know already that pi, although it is an irrational number, we do use an approximation for it, so 3.14. And if you multiply that times 2, so you will get 2 times 3.14, so it will be 6.28. And so that is what the circumference of the unit circle will equal to, based on the definitions that we have discussed before. So because the units of measure for S, the arc length, and R are the same, the ratio S over R has no units. It is a real number. Even if we were talking about units like 1 inch radius or 1 inch kilometers, once you divide the units, like let's say 1 meter for S, and then 1 meter for R. So then, even then, the units will cancel. And so that's why we could just say that that will equal to 1 radian. And that will be the angle measure. A lot of these things will make more sense once we start covering examples. Okay, so now let's go back to the full circle. And so we said that if we go one revolution is equal to 2 pi, provided we're working with that unit circle, and that means that the radius is equal to 1. We're not really concerned about the units here. So if we divide that circle into 2 equal parts, and so I'm just gonna divide them across the x-axis, so then this will be equal to half of a revolution. And so if the full revolution is equal to 2 pi, and we divide that by 2, we will get pi radians. And so with that, we're going to start forming a circle here. So let's say we start at 0. If we do one full rotation, that will equal to 2 pi. So this could be considered 0 or 2 pi if we go one full revolution. But now if we go a half revolution only, that will be considered pi. Now, what happens if we just go a quarter of that revolution? And so that would be starting from the positive x-axis, a quarter of a revolution, a quarter of a circle. That would be like dividing 2 pi by 4. And so 2 over 4, it equals to 1/2 or pi over 2 radians. So 1/2 times pi is the same as saying pi over 2. That's what we will be using. So let's place here 1/4 of a revolution, pi over 2. That will be here. Now let's do a 1/6 of a revolution. And imagine that we take what is considered to be pi, which is from here to here, and we divide that into thirds. So you can see here, this will be 1/3, 2/3, well, from here to here, and then 3/3. And it's not really to scale. So if we do that again here, that would be another third and another third of the other pi radians, because remember at the end we have 2 pi. So imagine this is pi and this is another pi. So pi plus pi equals 2 pi. So that would be kind of like 1/6 of a revolution. But the idea is that if you consider a full revolution, which is 2 pi, and divided by 6, you will have the fraction 2 over 6, which could be simplified to 1/3. And so 1/3 times pi is equivalent to saying pi over 3. And so that is what we will use as pi over 3 radians. And actually, it should be placed about here. And I'm going to tell you right now, pi over 3 is actually 60 degrees. So if we take the angle from here to here, that will be pi over 3. So to give you an example, and I know fractions are not everyone's favorite, but we will get used to them. To give you an example of the type of radian measurements that we will be using with respect to fractions, and also called, like right here, those are the most common angles. And so pi over 6 will be a sixth of the rotation of a circle. And so that is what we have here. So imagine if you were to divide your circle into 6, well, if you were to divide half of a circle into 6 equal parts. So here are 6 equal parts. But if you do that to the full circle, it will look like this. Like each quadrant is divided into 3 parts. But if we just consider one of those, that it's what we will call pi over 6. Now for the next one, moving to the right, we have pi over 4. So remember how we said that this will be 0, and this will be pi, and this was going to be pi over 2. So if we divide pi over 2 by 2, if we cut through it right in the middle, and that will give us pi over 4. So if we were to take half of the circle, which we already know is pi, and we divide it into 4 equal parts, each one of those parts will be considered to be to have the angle measure of pi over 4. Now, similarly, pi over 3, that is the one that we cover. that if you take half of the circle, which is considered to be pi, and divide it into 3 parts, each one of those parts will be pi over 3. Of course, we could consider this to be pi over 3. This will be pi over, actually 2 pi. Oops, 2 pi over 3. Actually, no, I started wrong. Sorry, my apologies. We should start with 0. This is 0. This is pi over 3. This will be 2 pi over 3. If we were to continue the rotation, that would be considered 2 pi over 3. And if we were to continue it all the way to pi, that will actually be 3 pi over 3, which if we simplify it, it would equal to pi, which is what half a circle is. And we could see that here as well. Half a circle, pi. Full circle, 2 pi. So lastly, we already covered it, but let's go over it again. So if you take pi, which is half of a circle, and you cut that in 2 equal parts, that will equal to pi over 2. If we were to continue, and because we will do this pretty soon. So if we were to label every single point based on those type of measurements, pi over 2's, this will be 0, this will be pi over 2, this will be 2 pi over 2, which is equal to pi, we know that. And the next one will actually be 3 pi over 2. And if we continue in the same direction, the very last one will be 4 pi over 2, which we simplify as 2 pi. So let's try to do that here with our circles. So the very first one, I want you to go ahead and divide it. So let's divide it in half, and then another half just to simulate the x and y axis. And so if we go one full rotation in the positive direction, we will have 2 pi. Now, if we go only half a rotation, this point will be considered half of 2 pi, which is pi. And if we go another pi to the same direction, it will be 2 pi. But we already knew that. Next one. We start here, positive x-axis, and we just go in this direction. And so that will be half of what this one was. So half of pi will be pi over 2. So a quarter of a circle is equal to pi over 2. And if we continue in that same direction, this will be 2 pi over 2, which is equal to pi. And if we continue, this will be 3 pi over 2. We leave it like that. There's no way for us to simplify it. And if we go one more time, that will give us 4 pi over 2, which is equal to 2 pi. But we already know that a full rotation or a full revolution is equal to 2 pi. So if we continue like that, and now let's go for this type of rotation. So from here to here, now I'm taking half of a quarter of a circle. And so half of pi over 2 happens to be pi over 4. So we divide the pi over 2 by 2 again. So it makes the denominator be 2 times 2, which is a 4. Like if you have a half and you divide it by 2, you get 2 quarters. So each half is a quarter. So that would be pi over 4. This will be 2 pi over 4. If I go another pi over 4 radians. But that one reduces or simplifies to pi over 2. And if we go another pi over 4 radians, we will get 3 pi over 4. Another one, and we will get 4 pi over 4, which is equal to pi. Another one of that same arc length or central angle, and that would be 5 pi over 4. Here, this will be equal to 6 pi over 4, but that is, if we simplify it, it will be equal to 3 pi over 2. So actually, I want you to keep an eye on the ones that I'm going to be highlighting because those are actually going to be very important when we build our own unit circle, which you will understand and memorize. So if we go another pi over 4 rotation, that will be, we were at 6 pi over 4, so this will equal to 7 pi over 4. And then one more pi over 4, and that will equal to 8 pi over 4, but that one is reduced to 2 pi. I'm going to write it here. So I'm going to highlight the ones that we're going to be using. Here for 4 pi over 4, we're not going to use that because we know that we could 4 over 4 is equal to 1. And so that we will cross that out, and this will just equal to pi, half of the circle. Okay, so that's going to be very important. Let's do a couple more, and then we'll move on. So let's divide those like that. And now what I'm going to do here is actually divide each quadrant or each quarter of a circle into 3 equal slices. Now, the ones that I'm going to highlight, that one, actually it's going to be like that. Those, we're going to draw them on this side of the circle. So there we have it. Okay, so now I'm going to get rid of this purple here. Okay. So what I'm going to do is start here by considering this to be 0, and I'm going to call this one pi. We already know that. And what I'm going to do is call this one pi over 3 because it is a third of half of a circle, which happens to be pi. So if we go in that same fashion, the measurement here is going to be equal to 2 pi over 3. Pi is going to actually be 3 pi over 3, but it reduces to pi. This one, the next one will be 4 pi over 3, And the one after that will be 5 pi over 3. And then the very last one will be 6 pi over 3, which we already know is equal to 2 pi. Okay, and that will be in the case that we go a full rotation. 2 pi, 6 pi over 3. So those are also numbers that we will be using. And so from there, the ones that will be happening here on the same lines, I believe it's this one. Okay, so for those, we're going to use the same numbers that I have highlighted in purple. So now let's talk about what the other ones will be. So the one here we already know is pi over 3. And this one right here will be pi over 6. Just to prove to you that the next one is pi over 3, it will be, if this was pi over 6, this will be 2 pi over 6. But of course, that is equivalent to pi over 3. The next one will be 3 pi over 6, which reduces or simplifies to 2 pi over 3. Then the one that we have here, it will be 3 pi over 3, which is equal to pi. And this will be, I'm sorry, I said that wrong. Yes, 3 pi over 3. But we were talking about pi over 6. And yes, actually, I'm going to back a little bit. If this was pi over 6, this will be 2 pi over 6. This will be 3 pi over 6, which happens to be pi over 2. We already knew that. That's 3 pi over 6. And then this one will actually be 4 pi over 6. That's the actual fraction that reduces to 2 pi over 3. The one here will be 5 pi over 6. And then here pi will be the same as 6 pi over 6. So then this one will be 7 pi over 6. So in fact, this one shouldn't be purple. This is the one that should be 8 pi over 6. But it reduces to this number, 4 pi over 3. I'm taking a lot of room there. And then if we keep moving in that same way, we will find that the one here is actually going to be 9 pi over 6. And that is actually, sorry, that will be here, this one here. And but that one reduces to 3 pi over 2, just like this one. Okay. Now the one that follows here, this one will be 10 pi over 6 or 5 pi over 3. That one right there. Then the next one, so this one we were at 10 pi over 6 or reduced to 5 pi over 3, and the very next one will be 11 pi over 6. This one is gonna be used a lot. And then of course the very last one that is equal to 2 pi will be 12 pi over 6. So you know from previous courses that the Cartesian plane is divided into 4 quadrants. And so we start where both x and y are positive. And so for those, we will have quadrant 1. And then here in quadrant 2, X will be negative, but Y is still positive. This will become very useful in the future. That will be quadrant 2. Quadrant 3, that happens when X is negative and Y is also negative. And then finally, quadrant 4 is where X is positive, but Y is negative. Now, speaking about angles and rotations like we were before, the quadrant 1 will cover angles that go from 0 to pi over 2, just like we see here. So that's the inequality that corresponds to it. Those are considered to be acute angles, the ones between 0 and pi over 2. If it is exactly pi over 2, it is called a right angle. Now, for angles that go in quadrant 2, that go past, they're greater than pi over 2, but they're smaller than pi, we consider those to be in the second quadrant. Actually, not this type. Only second quadrant because we're saying that they are greater than pi over 2. Second quadrant. And they're still smaller than pi over, that theta equals pi. And in fact, the ones that I'm circling also pi theta equals 0. And lastly, it will be the one here, 3 pi over 2. Those four, 0, pi over 2 pi, and 3 pi over 2, they are considered to be terminal angles. Not coterminal, but terminal. Terminal angles. Okay, so third quadrant, that takes the angles that are bigger than pi but smaller than pi over 2. And then finally, quadrant 4 will take the angles that are bigger than 3 pi over 2 but smaller than 2 pi. Now, if it goes a full rotation, then it will end up in the same position where it started for a full revolution, and that will be equal to 2 pi. So, from here, we've been discussing about initial side, terminal side. So two angles are coterminal when they have the same initial and terminal sides. For instance, 0 and 2 pi are a coterminal. So in fact, I would like to say this, well, yeah, that's okay. So let's go ahead and check this by drawing what pi over 6 will be. Pi over 6 will be over here, a sixth of half of a circle. And so 13 pi over 6, that is actually, I could break this down into two fractions where one of them will be 2 pi over 6 and the other one will be 1 pi over 6. Now, instead of writing the 1, I'm going to be just writing pi over 6. So that is the same thing. So if I was to use pi over 6, like I already have it drawn here, but then I go another 12 pi over 6, which is actually equivalent to 2 pi. That would be like a full rotation of a circle, and I will end up here. And so those two sides that are, and I will actually like to define it this way. Two angles are coterminal when they share their terminal side. So we could have angles that are coterminal to any other given angle by adding or subtracting 2 pi, which is 1 revolution. And as we demonstrated with this example, so if we add, this will be 1 revolution, 2 pi, to the first angle in question, pi over 6, and we got 13 pi over 6. So we could say that those two angles are coterminal. And in fact, if we keep adding rotations to it, we will just end up with another coterminal side. So for instance, if we were to say, let's let n, this variable here, which is an integer, equal to 2, so then it will be something like pi over 6 plus 2, and then we substitute n with a 2, because that's what we said here, times pi, and so that will be the same as pi over 6 plus 4, because 2 times 2 is 4 pi. That will be equivalent to pi over 6 plus, if this has a 1 and we want to turn it into 6, we will multiply by 6 over 6. And that will give us 24 pi over 6. And that is actually equivalent to 25 pi over 6. So that could be another example of a coterminal angle. So for example 1, we are going to find a coterminal angle, and the angle that we see here, which is 13 pi over 6, it just happens to be an angle that we already used on the previous slide. And so to find an angle that is coterminal to it, and let's go ahead and trace it here. So that would be an angle that starts on the positive x-axis, and we go a full rotation. And I say a full rotation because 13 pi over 6 could be breaked into two angles. One will be 12 pi over 6, and the other one will be 1 pi over 6. So we know this one from the previous example that it is equal to 2 pi. So that will be a full rotation, a full circle, and then we go an extra pi over 6. And so I do like to teach by showing the visual representations. And so because it kind of like helps you create an idea, and you will get used to that, you do have to subtract, because sometimes to find a coterminal angle, you have to add 2 pi or subtract 2 pi. So if we take that 13 pi over 6, and we subtract 2 pi, which we will be equal to 13 pi over 6 minus 2 pi is equivalent to 12 pi over 6. And so that will give us pi over 6. And so that is this little angle, again, in standard position, starting from the positive x-axis and just going pi over 6 in the same direction. So those two angles, 13 pi over 6 and pi over 6, because they do have the same terminal side, this is a terminal side, they are called coterminal. Just like a co-worker, a person who works at the same place as you do, a coterminal angle will be an angle that has the same terminal angle as another angle. So two angles are coterminal if they share the same terminal angle. For negative angles, such as the one that we have listed here, to negative 2 pi over 3, what we will do, and let's pretend that we don't have the graphical representation of it. So let's read the question. So it says, for the negative angle negative 2 pi over 3, add 2 pi to obtain a coterminal angle. Sometimes your homework or your exams or your quizzes will ask you for a coterminal angle, and it might get a little more specific and say a positive coterminal angle. So when that happens, and it's actually easier to deal with positive angles, you will be adding certain, you could be certain that you will be adding 2 pi if you have a negative angle and you want to get a positive coterminal angle. So in this case, we have 2 pi with a denominator of 1, so we're going to have to multiply top and bottom of 2 pi by 3. So times 3 times 3. And so that will give us 6 pi over 3. So we do have to do that so that we can have the same denominators. And so now we have a negative 2 pi plus 6 pi, both of them, over 3. And so that will equal to positive 4 pi over 3. So now let's trace both of them. So the first one that I'm going to trace, well, let's use the yellow highlighter, is going to be 2 pi over 3. So that is going to be in the negative direction, so clockwise. So still we start with the positive x-axis, but we move in this direction, and that will be the negative 2 pi over 3. Now what happens if we go, again, start from the positive x-axis, but now we go in the counterclockwise direction this way, but we stop at the same terminal side of that angle. And so that will be equal to the 4 pi over 3. And you could check that if you go back on your notes. So this is something that perhaps you have heard about since elementary or middle school or high school, that two angles happen to be complementary. If the sum of those two angles, if you add them, you get pi over 2, or just to remind your refresh your memory, that is equal to 90 degrees. So if you add two angles, like let's say 30 degrees plus 60 degrees, you will get 90 degrees. So those two angles, 30 and 60, are supposed to be complementary. And although we're going to cover this in a minute, I just want to show you that if we use the same but in radians, it will be 30 degrees is equivalent to pi over 6. I will teach you how to do that in a few minutes. And 60 degrees is equivalent to pi over 3. So if we add those two numbers, the common denominator is going to be a 12. And so for pi over 6 with a 12 on the bottom, we will have to multiply by 2 and 2. So that will be 2 pi over 12. And for pi over 3 to have a 12 on the bottom, we'll have to multiply by 4, not 3, but 4. 4 and 4. And so that will give us 4 pi over 12. So if we add those two, we will get 6 pi over 12. And if we simplify this fraction by dividing by 6, 6 pi divided by 6 is equal to pi, and 12 divided by 6 is equal to 2. So remember, pi over 2 is located, it's a quarter of a circle. So it's positioned right here, pi over 2, which you know that a right angle is the same as 90 degrees. So complementary angles could either equal, the addition could equal to 90, or the addition could equal to pi over 2. So just like we have complementary, we also have supplementary, and those are angles when you add them, the sum is equal to pi or equal to 180 degrees, which is what we call a straight angle. 180 degrees, or in radian measure, pi. And that is if we were to add those two. Let me give you an example. Let's say that alpha is equal to 60, and then beta is equal to 120. So if we were to add those two angles, we will get 180. That's what we call supplementary. Now, a second way to measure angles is in degrees, but you've been using this for a while, since elementary or middle school. And so a measure of 1 degree is equivalent to a rotation of a circle divided by 360. And so, or 1 over 360 of a complete revolution of a circle. So if you didn't know, one complete circle or one complete revolution is equivalent to 360 degrees. And this is why we say that 1 degree is that full revolution, but divided by 360. So if a full revolution is equal to 360, if we were to divide 360 by 2, we will get 180. And so that is what we called half revolution. So half of 360, 180. And a quarter of a revolution, so if you divide 360 by 4, you will get 90. So that's what we called a quarter of a revolution, and so on. So because 2 pi radians corresponds to one complete revolution, one full complete revolution, in degrees, that is equivalent to 360. So if we were to divide 360 by 2, we will get 180. And if we divide 2 pi over 2, we will get pi. And let's not forget the units, those will be radians. So based on that, we are going to construct our unit conversion factor. So if we're saying that 180 degrees is equal to pi radians, and if let's pretend you have 180 divided by 180. So now what I'm going to use, instead of 180, I'm going to write the equivalence in radians, and that will be pi radians. And so I'm going to replace that, but I'm going to leave the 180 here on top. Just like I did that, we know that pi over pi is also equal to 1, right? Just like this one, equal to 1. So let's now replace pi with 180 degrees. And we can do that because of this statement. So if we just write as a fraction here, these two things that we have here is what we called our unit conversion factors. So 180 degrees divided by pi radians is equal to 1, just like pi radians divided by 180 degrees is also equivalent to 1. And that is also what we have here. And so it depends what you're trying to convert. So if you are trying to go from degrees to radians, then you need to use the one that will have degrees on the bottom. And I'll tell you why, because you want to cancel those units, radians. And we will see it on the following examples. And if you want to go in the other direction from radians to degrees, then you want to have the unit factor that contains radians on the bottom so that you can cancel the units. So just as a quick reference, we have here what 360 degrees is equivalent to 2 pi radians. 180 degrees, which is half of a circle, is equivalent to pi radians. 90 degrees is equivalent to a quarter of a circle, or pi over 2 radians. 45 degrees is equal to a quarter, not a quarter, well, a quarter of pi, or an eighth of a circle, and that is equal to pi over 4th. And also we have pi over 3, which is 60 degrees, equivalent to it. And we have 30 degrees, which is equal to or equivalent to pi over 6 radians. Now, those two that I left at the end are kind of confusing. I want you to remember this. If we compare 30 degrees and 60 degrees, which one is bigger? 60 degrees is bigger. So the fraction, if we compare the two in radians, pi over 3 and pi over 6, which one will be bigger? And the answer is the bigger will be pi over 3 because it's being divided by a smaller number. So imagine if you have a pizza and you invite 3 friends or you invite 6 friends. When would you get a bigger piece of the pizza? If you invite only 3 friends. So the smaller the denominator, the bigger the fraction. The bigger the denominator, the smaller the fraction. So use that to remember that 30 degrees is pi over 6 and 60 degrees is pi over 3. So let's move on. So when no units of angle measure are specified, we're going to imply that it is radians. So don't think that because they forgot the units, they meant to say degrees. So if we just say theta, remember Greek letter, equals 2, that actually means 2 radians. And just to give yourself an idea of what 2 radians is, remember this is pi, and we know the approximation for pi is 3.14. So this is supposed to be 3 radians. So 2 radians, it should probably be, I don't know, maybe there, from here to here. That will be 2 radians. If you're in doubt, you could always convert to degrees and, see if you're correct. Okay, so how do we convert from one to the other? So, like I said before, the unit factors, we have them here. Well, we're actually using the same. So remember, your unit factors could be pi over 180 or 180 over pi radians, 180 degrees over pi radians. So either or. Now, we decided to use the one that contains degrees on the bottom, which is this one, because we want to cancel the units of degrees, as you can see here on the example. So if we were to multiply 135 degrees by our unit conversion factor, 135 degrees times pi radians will equal to 135 pi, and you can see here degrees cancel, and then 1, because that is the denominator of the integer, 1 times 180, that's how we multiply fractions straight across, it will be 180. So if we divide 135 and 180 by 45, we will get 3 pi over 4. Now, if you're not sure on how to simplify it, you could start by dividing 135 by 5, and you will get 27, so it will be like 27 over 180 divided by 5 will give you 36. And so you could recognize those two are divisible by 3. And 27 divided by 3, or actually let's divide them by, well, let's divide by 3. So 27 divided by 3 will be 9, so 9 pi. 36 divided by 9, it will be 4. Okay, yeah, I did something wrong here, so, okay, let's revise that. So I'm going to use the calculator. Oh, okay, I see what I did. So I had 180 divided by 3 wrong, so that should have been 60. So let's go back here. 135 divided by oh, okay, so 135 divided by 3 is 45. And then 180 divided by 3 is 60. Okay, and then we can divide by 5. 45 pi divided by 5 is 9 pi. And then 60 divided by 5 is 12. Now we can divide by 3. 9 pi divided by 3 is 3 pi, and 12 divided by 3 is 4. So that's another way that you could simplify a fraction. Web sign will always require you to simplify your fractions. Now the next example, 540 degrees, we use the same unit conversion factor. We want to have degrees on the bottom so that we could have that degrees over degrees, which will equal to 1. And that's why we say they cancel. They don't disappear. They just equal to 1. So that's how you know that if you're going from degrees to radians, you want to have the unit conversion factor that has degrees at the bottom. So if we multiply this straight across, 540 times pi radians, it will be 540 radians. And yes, I forgot the units here and here. And that will be divided by 1 times 180. And so if we just divide 500 by 180, I believe that's equal to 3. So this will be equal to 3 radians. And actually, I want to correct this. It should be 540 times pi. So it's 540 pi radians. So if we were to simplify that, 540 divided by 180, yes, it will be 3, but we still have the pi over there. So just to give you a visual of what that is, it will be a full rotation, that's 2 pi, and then another half rotation, and that will be the 3 pi. So this will be 0 pi, and then you keep going, 2 pi, and then you keep going, and that will be 3 pi. So that will be 3 pi radians. So radians, and I know there's no example here, so let me just make up one. Let's try pi over 4. So pi over 4, and let's say we want to convert this to degrees. So let's do that. So we have radians here, and we're going to use the conversion factor that has pi radians at the bottom, because if we want to convert to degrees, we want to cancel the units radians. So that's how you know. And what goes on top? Well, 180 degrees. So if we multiply straight across here, we will get the units cancel, but also pi will get canceled. And we will get 180 degrees divided by 4. And so 180 degrees divided by 4 is equal to 45. Now, I want to move on because I'm making this video way too long. So here, the radian measure formula, S over R, can be used to measure the arc length along a circle. And so just like we have that formula, theta is equal to the length of an arc divided by the radius. Remember, we did that at the very beginning. So if we were to take this R across the equal sign, it will be multiplying, right? Like this. Like that. Or you could imagine that I'm multiplying by R on both sides, so it will cancel here, so then we get R theta, which is what I have here. And so R theta is what we're going to use to find the length of a circular arc. And this doesn't have to be of an arc that has to be 1 radian. It could be of any measure. But the condition here, and I cannot stress this enough, is that the angle, it must be in radians. So if your question is giving you something in degrees, you must convert it to radians first before you could apply this formula. So whenever you study for your exam or your quizzes, please remember that. I am highlighting it here so that you do the same thing. So let's solve this example. We have a circle with a radius of 4 inches. So r is equal to 4 inches. And we need to find the length of the arc. So S is our unknown. And we have a central angle. Remember, central angle is the angle whose center is at the center of the circle. And the central angle is intercepted. The arc is intercepted. So this is the arc. So the arc length means, like, if you were to straighten that sector of the circumference, it will be, that's what we're looking for. We're looking for, like, how long will that be based on the center angle being 240 degrees and the radius being equal to 4. So we could definitely use a formula, but first we need to convert our angle into radians. And so we want to cancel degrees. So we need to use the unit conversion factor that has degrees at the bottom so that we could cancel those units. And so what do we need here on top? That would be pi. So we're going to have 240 times pi, and here we will have 180. And actually, I forgot, here it should say radians. That would be the measure, the unit. So 240 divided by 180, we could cross out the zeros, so we have 24 over 18 pi radians. And let's see, we could divide that by 3. Yes, so 24 divided by 3 is 8. And 18 divided by 3 is 6. Oh, and now we can recognize both numbers are divisible by 2. So 8 divided by 2 is a 4, but let's not forget pi. And 6 divided by 2 is a 3. So that will be the angle measurement. So this theta that we have here, that should be equal to 4 pi over 3 radians. So this angle measurement is the same as 4 pi over 3 radians. Now remember, it's a must that you convert your angle measurement into radians. Now we could go ahead and apply the formula r theta. And so the arc of that length is going to be equal to the radius, which is 4, times 4 pi over 3. And so that will equal to, remember, we multiply straight across, so that will be 16 pi over 3. And that is just something we cannot simplify any further. And this will be if WebAssign happens to ask you for the approximation, then go ahead and put this into your calculator. Just be careful to not use an approximation of pi, such as 3.14. You might want to look for that button on your graphing calculator that it has pi on it, so that you could get a more accurate answer and not get it counted wrong because of rounding when you do your homework on WebAssign or take a quiz. Okay, so, oh, actually, this was the sheet that I should have used to solve the example. But hey, now we know that 16 pi over 3 If we were to put it on the calculator, we will get that. So this was 4 times 4 pi over 3 and 16 pi over 3. If WebAssign asks you for the exact answer, this will be the exact answer. Now, if they ask for an approximation, that will be the 16.76 inches. And so that will be the length of the intercepted arc, which will actually be, I'm going to go back to the circle so we could see what that would be. And that will be this one here. That is the one that is 16.26 or 76 inches. Okay, so finally, we have two applications for this section, and one of those is the linear speed, and the other one is the angular speed. And so the formula for the length of a circular arc can help you analyze the motion of a particle moving at a constant speed along a circular path. So consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed, which we'll use v of the particle, is considered, and remember this is linear speed, is going to be the same as the arc length divided by time. And that's what we have here. And so imagine that you have a circle and we just want, we have a particle that starts moving from here around the circle in certain time. And so to calculate the velocity, or I'm sorry, the linear speed of that particle, we will have to measure the length that the particle cover, the segment or the arc length, divided by how long it took for that particle to be there. And that will be the linear speed. But now, if what we want is the angular speed, and the word angular, it refers to the angle measure. So we don't want to know the length of the particle cover. We want to know how many angles the particle cover based on the central angle definition. That will be considered the angular speed. And so here again, theta will be the radian measure, and we will use the lowercase Greek letter omega, it looks like a W, to denote the angular speed. And just finally, I wish we had an example in this section, but I will cover one on Wednesday. A sector of a circle will be kind of like a fraction of the area. So it will be not just talking about length, but area. That will be a sector. And here we have the formula to find the area of a sector. And like I said, I will definitely include some examples on our next lab session. So the formula will be here, and to find the area of a sector, it will be half of the radius squared times theta, and make sure that again theta is measured in radians. So this is the end of the lesson.